partial fractions decomposition, just because it shows up a lot when we're trying to deal with integrals that involve rational functions. So the idea and the intent are very simple. All we're trying to do is we have a complicated fraction, and we're trying to decompose it into a couple simpler fractions. Okay? The first thing you need to make sure you check before you even start the process is to make sure that your fraction is indeed proper. In other words, it's bottom heavy. The degree of the bottom polynomial, the polynomial that makes up your denominator, is higher than the degree of your numerator. Okay? So once you make sure that that is true, then the process is very simple. All you're doing is taking the different factors of your denominator and creating different fractions. The reason you have to do that is because the function on the left-hand side of the equation, if you think of this as an equation, has two poles, one at A and one at B. Remember poles from Algebra 2 where the function is discontinuous, the holes in the asymptotes? Well, you have a pole at x equals A and one at x equals B. And if this function is to be equivalent to this guy, then he also needs to have a pole both at A and B. Otherwise, there's no way its graph is going to look like his. Okay? So the only really two tricky things is this case and this case. Namely, when you have a repeated factor, a factor that on the outside, the whole thing is raised to a power, and when you have a factor that itself is quadratic or cubic, or something higher than that. So let's deal with this one first. When you have a factor that's raised to something, so here we have x minus a all raised to the second. It's not just x squared minus a. That's this guy. Okay, there's a big difference on sort of the treatment that we're going to impose. But if you have a factor that's raised to a power, all you're going to do is repeat that factor that many times, and you're going to square or cube the denominator. So what I mean is if you have x minus a squared, you're going to have a term that's just x minus a, and then you're going to have a term that's got the denominator x minus a squared. If you had a cubic, you'd have this guy, plus a c over x minus a to the third. Okay? And your top doesn't change. Remember, your numerator can go as high as it can before reaching the degree of your denominator. Okay? So if your denominator is linear, which is the case here, your top can only go up to a constant. But here, we have this other special case where your factor isn't linear. So this factor is linear because the power of x is 1. But here we have x squared plus b. Now here, our numerator, sort of our placeholder general numerator, can go up to a linear factor, right? It can have bx. It doesn't just have the c. It also has a linear factor. If we had a cubic factor, if we had an x to the third plus bx squared plus cx plus d, then our numerator would be of the form ax squared plus bx plus c. Because again, it can go up to one level below the degree of the denominator. Okay? So let's go ahead and do an example really quickly to figure out if we know actually how to set it up. It's really, the process is in sort of two steps. Number one is getting the general thing right? When we're about to decompose this, we're going to write out what we think it's going to look like, and then actually solve for the coefficients, right? Namely a, b, or a, b, and c. So getting the first part right is extremely important, because otherwise then you're just going to get it wrong if you don't get the general form right. So we're going to focus, and we're going to say, okay, well, I have a linear factor, x minus 2, nothing important there. But then I have a quadratic factor, so I have to keep in the back of my mind that when I write out that fraction, I make sure to allow this guy to be able to go up to a linear term, okay? So first, let's write out the x minus 2 fraction. Well, it's going to be very simple. It's just a over x minus 2. It's a linear factor, nothing important there. But now I'm going to write my second fraction, x squared plus 2x plus 4. And now this guy can go up to a linear factor. It's not just a constant. So I'm going to have my bx plus c. It's not just the c, but it's going to be bx plus c now because of the x squared. So now what I'm going to do is actually try to solve. Now I have an equation, and I'm going to try to find out a, b, and c. Remember, this equation has to be true for all x. If this were an equation and we had 3 unknowns, we wouldn't be able to solve it. But since it's an equation that has to be true for all x, now we have, we can actually solve it. So I don't like dealing with fractions, so what I'm going to do, and I suggest you do the same thing, is to multiply by this denominator, multiply both sides by that denominator. So what's going to happen is, on the left-hand side, I'm going to be left with 10x squared plus 12x plus 20, since if I multiply this whole side by this denominator, they're going to cancel each other out. Then on this side, my a over x minus 2 is going to cancel the x minus 2, so I'm going to be left with a times x squared plus 2x plus 4. Then this term, this guy will cancel him, but the x minus 2 will remain, so I'll have bx plus c times x minus 2. Okay, so now there are a couple ways to solve this guy and find out a, b, and c. My preferred way is to do the following: to choose values of x that are very convenient, that are going to get rid of either this guy or that guy. Watch, if I choose x to be equal to 2, okay, then on the left-hand side, I'm going to have 10 times 4, 40, plus 12 times 2, 24. So 64 plus 20, 84 is equal to, and then I'm going to have a times 2 squared, 4 plus 4 plus 4, 12, plus, but then look at this. This whole thing just goes away because the 2 minus 2 gives us 0. Okay, that's why I chose x to equal to 2. You make convenient choices of x so that one or more of your factors sort of get knocked out. So now I can immediately see that a is going to be 7. But then, if I wanted to do the same thing for him, it's a little harder because that's a quadratic, and I would actually have to solve the quadratic equation. And I can already tell, since these two terms are being added to x squared, that this quadratic is actually going to be above the x-axis, so it's going to have imaginary roots. So I'm not going to go down that road. I'm going to sort of show you another way that you can solve these guys. And that's by comparison of coefficients of the same term. So I'm going to take x squared, and then I'm going to compare the left-hand side coefficient and the right-hand side coefficient of x squared. On the left-hand side, I have 10. And on the right-hand side, I'm going to get a contribution here from a, and I'm going to get a contribution from here, b, when these two guys are multiplied by another. So a plus b. Well, a is just 7, so it's 7 plus b is 10, so b is 3. Okay? Then I'm going to move down to x. I'm going to compare coefficients of x. On the left-hand side, I'm going to have 12. And on the right-hand side, I'm going to get a contribution from right here, 2ax, or just 2, the coefficient. And then over here, I'm going to get a contribution from minus 2 times b. And also a contribution from this guy, plus c. Right? So, well, I know what a is. It's just 7, so this is 14. Well, I know what b is. It's 6, so this is minus 6. Or this is minus 8, or just this is 8. So 12 is 8 plus c, or c is 4. Okay? So now I can go back to this guy and say, well, a is 7, so this is going to be 7 over x minus 2. bx plus c is going to be 3x plus 4. And that is it. That is our answer. Okay? So it's not hard. It's just sort of a lengthy process, and you're going to have to make sure you don't make any mistakes in your algebra. There is one more thing I wanted to mention that kind of goes along this, this partial fractions business, and it's when you have integrals of this form. It's just a little trick that sort of you're sometimes expected to perform, but you're not necessarily taught. So when you have integrals of this form or fractions of this form, you can do a little trick. It's not really, and it doesn't have anything to do with partial fractions, but usually these problems show up in the same unit, so I'm covering it here. What you can do, because you can't really do this integral just by itself, okay? So what you can do is play a little trick and add one or subtract one and then add one right back to the numerator. So do -1 plus 1, and then you write the plus 1. Okay? And what this is going to do is give you exactly what you want to separate this, this fraction, because you can now do this. And you can just write this as plus 2. So now I have x minus 1 plus 2 all over x minus 1. Well, I can group these two. I can split this fraction if I want to. I can split the numerator. I'm not splitting the denominator. Remember, numerators I can do. So I'm going to write this as x minus 1 over x minus 1 plus 2 over x minus 1. Okay? So now this guy is just 1. And he's just 2 over x minus 1. And I can integrate them both very easily. I can integrate the 1. It's going to be an x. And the 2 over x minus 1 is just going to be 2 ln absolute value of x minus 1. Right? So this is a sort of a random thing, but it shows up not often, but enough that it sort of can make a difference on your tests and quizzes. So there you have it. That's partial fractions and just one random trick.